Bam! Mr. Taru. In this algebra lesson, we are going to continue learning how to model real-world situations with linear functions. This is actually sort of a part 2 video, if you will. The example is a little bit more complicated than the initial or part 1 lesson that you'll find a link to in the description of this lesson. So in this video, we're going to read this real-world scenario. We're going to have to analyze, after identifying the independent and dependent variable, what the slope of this line is going to be, this linear function is going to be from the table of values, because the reading of our example is not going to give us any indication of what the slope is, like the previous lesson that we went through. Then we're going to what? We're going to figure out or calculate what that slope is. We're going to be interpreting the slope in context of this problem because, if this is the first lesson you've watched, you haven't heard me say this, but like I said in the previous video, while slope is rise over run or change in y over change in x, neither one of those definitions are really good for interpreting what slope means in context of a word problem. For that, we have to know that slope is the average change in y, the dependent variable, per 1 unit of change in x, the independent variable. We're then going to either learn or relearn or review how to, depending on what you've studied, how to write the equation of a line with a given point and a slope, which we're going to have to find on our own in just a moment. We're going to be interpreting the y-intercept of the line. We're then going to graph the line on an x and y axis, making sure we use proper labels and scales on those x and y axis. And then we're going to, use the linear function that we come up with to find out how long does it take for the parachuter to land. Now, this lesson, like I just alluded to, I believe in my introduction, this is the second take of my lesson, in the reading of this problem, it doesn't give us all the information that we need. It doesn't give us any indication of what the slope is going to be like the previous lesson I just did. The language of that example did give us the slope. We're going to have to figure out what it is from this table of data. Now, this table of data, though, is going to form a perfectly straight line. We are not going to be relying on a graphing calculator to come up with what's called a least squares regression line, which is really more realistic, to real-world data. Real-world data generally does not follow a perfectly linear pattern. Thus, we come up with a linear model that may hit some of the points and actually may not hit any of them. If you need to know how to come up with a least squares regression line to model real-world data, I have a link to that lesson down in the description of this video as well. Okay, but for now, let's get to this one. At 3,500 feet, a skydiver jumps from a plane and immediately deploys her parachute. I'm saying immediately deploying her parachute so that we can kind of have a reasonable assumption or setting where we have a setting where it's reasonable to think that this data is going to follow a linear pattern. Information about her descent, is below. Because if she didn't deploy her parachute, she'd be falling much faster. Okay. Well, in the original problem, and like I've been saying with my algebra lessons, when you try to identify the independent and dependent variable, what's going to be on the x-axis, the independent variable, and what's going to be on the y-axis, the dependent variable, that the independent variable is the input value, and that's going to need to be how we think of an independent variable for this particular problem. Because another way of thinking about an independent variable is a variable that you have some control over. Well, this person free-falling from a plane is not really going to have any control over the number of seconds that they're descending with the aid of a parachute or the altitude. Kind of like if you're working for a job that you get an hourly wage, you have some control over maybe, say, how many hours you work in the week. So when you have a problem that maybe you can't easily identify a variable that you think of, well, if I was in that setting I could control that particular variable, then you need to look at it a little bit more. Like if your problem, like this one, has a variable of time very, very often, you can almost say all the time, except I'm sure there's some examples where someone could prove me wrong there, the time is going to go along the x-axis. The time is usually thought of as the independent variable. So our independent variable is going to be my first column here. we're going to identify what that quantity is or what that variable is and what's the unit of measure. And I give us a hint here that the unit of measure is in seconds, so this first column is going to be a variable of time. The time it takes to, basically descend from the plane and land on the ground. And then we have these other values, and if we look at these are all in the thousands except for this last one, which is 510. We go back and read the problem, and it says that we're initially going to jump out of a plane whose altitude, height, above the ground, is 3,500 feet. So it seems that, this second column would be the altitude of the parachuter. And the unit of measure is going to be, because of how the problem reads right there, is going to be in feet. I just realized I started to highlight, those blank spaces or open values in the table. Going back in the reading, how would you identify that? At 3,500 feet, a skydiver jumps from a plane, and you can think of that setting. Well, of course, you're going to start falling, so your altitude is going to change. So the two variables that are being compared are that altitude, starting at 3,500 feet, and I'm assuming going down from there, right? And it doesn't say anything about time, but then you go to the table of values and it says something about seconds, indicating that that is going to be the other variable of interest. And then you'll need to look at those two and identify what's the independent and dependent variable. Would a linear equation, a linear model, a linear function, be a good model for this scenario? Is a line going to model this data? Now, this is made up again as these points are going to form a perfectly straight line. A linear model with truly real-world data may hit some or even none of the points. So just be aware of that. Here it will. So what I'm going to do is I'm going to be remembering, okay, lines, I know what those look like. Lines are kind of like, they don't change direction. They're straight. So if they don't change direction, then it doesn't matter, or should not matter, which 2 points I use to calculate the slope. I should be getting the same answer. So if I'm going to look at this table of values and identify if a linear model is a good fit, or a good model for this data, I'm going to find a couple of points and calculate the slope. So just referring to my notes to make sure I have something to check my work with, let's do 15 and 3,155. And let's call that x sub 1, y sub 1. And again, this is going to be my independent column, my x, and this is going to be my DEP for dependent column. And let's see, what else did I use? It really doesn't matter, but again, I want to have something to be able to validate my work with, because I've already done this. X sub 2, y sub 2, let's let that be our second point. Now, slope is rise over 1, or change in y over change in x. So y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Well, if this is my labeling, then I'm going to have, let's see here. Well, y sub 2 is going to be 2511 minus y sub 1, which is going to be 3155 over x sub 2, which is 43 over 15. Excuse me, 43 over 15. How about x sub 2 is 43 and x sub 1 is going to be 15. And now I'm looking at my notes and I'm realizing, yeah, well, the first time I worked out the slope, I didn't use those two particular points, so I'm going to have to do the subtraction and division in my head. So let's see here. 3155 minus 2,000 is going to be, what's that going to be? 1,000, because I'm going to take 2,000 away from this. So 1,155. 1155 minus 5. Well, 11 minus 5 is going to be 6. So 1155 minus 500 is going to be 655. And now 655 minus 10 is going to be 645. And 645 minus 1 is going to be 644. And my, well, let's get the 644 down there before I forget what I said. Now, the larger, I'm combining two numbers, one positive, one negative. Well, when you're adding numbers with different signs or subtracting two numbers, you want to subtract those numbers and keep the sign of the largest absolute value, and that's going to be the 3155. If I ignore the negative, that's the bigger number, but it is negative, so that's going to be negative 644 over 43 minus 15, well, 43 minus 10 is 33, and 33 minus 5 is going to be 28. Now, that division, though, I can't do in my head. So what I'm going to do is I'm going to step off. I'm going to make sure that I didn't make any mistakes and calculate the slope of this. And then I'm going to identify or use a couple more points and recalculate the slope with those two. And if our slopes are equal, then I'm not going to connect. I'm not going to work out every single combination of all 4 of these points and check every single one of these slopes. But I think if we do it a couple of times and we get the same slope twice, then we're safe. A linear model is going to be a good fit. Bam! Yes. My calculations, my mental work was right, and the slope came out to be negative 23, which matched my notes that I've already done. And I picked a couple of more points and just showed you that I'm picking 2 different points. I used my last one here, 130, 510, and 43. Is that the one I used? No. 80 and 1660 did y sub 2 minus y sub 1 over x sub 2 minus x sub 1, got a slope of negative 23 again, and got the same answer, so I'm pretty sure that a linear model is going to be a good fit for this data. Okay, now interpreting the slope, the average change in y per 1 unit of change in x. This is the real definition of slope. Yes, it's rise over run. Yes, we have a formula over here, change in y over change in x. But I believe the textbook, the Algebra 1 textbook that our school system is buying into now, gives an alternative idea of slope of unit slope, which is change in y over just simply 1 unit of change in x. And I'm writing the average change in y because, well, what if you were using, maybe if you had like real data that wasn't exactly straight, but you noticed sort of like a linear cloud of points that you then wanted to run a least squares regression line through, that you need to come up with the use of by using a graphing calculator or some kind of computer software. Well then, with those y values, not just the y values, but with those points not forming a perfectly straight line, then you need to bring in that extra word of average change in y per 1 unit of change in x. So how do I interpret the slope of negative 23 in context of this problem? Well, y is altitude and x is time in terms of seconds. So one way you could say this is her altitude is changing by negative 23 feet per second. Okay, and the word per and then plus, there's no unit of measure in front of the second, and there's no s on it either, so that kind of implies that my change in x is going to be 1. So her altitude is changing by negative 23 feet per second, or for every 1 second of time that goes by. And I have to include the negative. That negative notation indicates a movement down, that her altitude is decreasing. And on the xy axis, movements down and movements to the left also are generally identified as being negative movements. Okay, so, and when you measure units, like when I measure my weight, or how tall I am, or how far I've traveled, it's kind of like really no such thing as a negative measurement except indicating direction. So her change in altitude is 23 feet. It's negative because she's going down again. There's no language in this sentence that would indicate, other than reading the problem and knowing that it's a parachute problem, that this change is going down, that her altitude is decreasing, or that she's falling with the aid of that parachute, so of course she's falling slower and it's a safe descent. Now if I reword this, there's a way I can, maybe I can write the, rewrite that 23 and not require a negative number. So maybe we could say this, descending is sort of language for, altitude is decreasing, so she is descending at a rate of 23 feet for every 1 second. Or just for every second, or per second would really be a little bit cleaner still. I just wanted to put a little bit slightly different language. Now here, I'm indicating that, you know, her altitude is falling. Okay, she's not like an airplane that's taking off and her altitude is going up. She is descending, she is falling, and thus saying that she was descending and then having a negative rate, that indicates a downward direction. The negative on the 23 would indicate a downward direction. And it's kind of like when you multiply two negatives, they multiply to give you a positive answer. So that would be incorrect. It would be incorrect to say she's descending at a rate of negative 23 feet per second, because those two negatives again would cancel each other out. So that's another way of wording or coming up with an interpretation of the slope for this problem. And also, I've been stressing, I've been doing a lot of, in my early algebra lessons, a lot of work with you guys about these linear functions, and I've stressed this before. Let me just make sure that I do this again. When you're reading a word problem and you see something, let's say rate of change, I'm traveling at 50 miles per hour, or in this case maybe, or well, not in this case, in our previous lesson where we talked about somebody working on commission, they were getting an extra $200 in commission per car sold. So that language here of, you know, something per something else, oh, that was the previous wording. I could have said, she is descending at a rate of 23 feet per second. That per word in there would be an indication that you're looking at a rate, or if you saw that in the original problem, you could know that the number near that expression is probably going to represent slope. So there's okay, I'm repeating myself now, there's two interpretations of slope. Let's move on to, let's see here. Let's come up with the function. Let's write the equation that actually describes this data, the equation of the line that goes through these 4 points. No. Write a function that models this scenario. How do you write it? The equation of a line given a point and a slope. You can use the slope-intercept form, y equals mx plus b. I prefer to use the point slope, which is going to be y minus y sub 1 is equal to m times x minus x sub 1. And when we write this form, which by the way, if I were to divide both sides by x minus x sub 1, I would have y minus y sub 1 over x minus x sub 1 equals m. So the point slope form of a line is just another version of, or another way of writing slope. And where we're going to put the points, I hope you already know this, but just reviewing in case you don't. The numerical values of the 1 point that we're going to use and the slope are going to go in for x sub 1 and y sub 1 and m. So now we have y minus 3,155 is equal to negative 23 times x minus 15. Now let's go ahead and get this into slope-intercept form, y equals mx plus b, because I want to graph this linear function. I want to graph the model that represents this real-world data of this young lady who was skydiving. So y minus 3,155 is equal to negative 23 times 1 is negative 23x. And now we're going to have negative times negative, which is positive, but what is 23 times 15? Well, let's see here. That's the tens place, right? So 10 times 23 is 230. And then we have 5 times 20, that's the tens place, right? 5 times 20 is going to be 100, and 5 times 3 is going to be 15, so we have 115, which is going to come out to be 345. I'm just thought I would, verbally go through my mental math, or at least the way I work it out. If I were to write, and you'll notice that when I do addition and subtraction and multiplication, I'll tend to do my work from left to right, and that way I don't have to do any carryover and borrowing, because I find that to be very hard to keep track of in my head. If I did 23 times times 15 on paper, I would be doing 5 times 15, or 5 times 3 is 15, carry over the 1, 5 times 2 is 10, plus the 1 is 11, and so on, and finishing my work up, like we know how to do, working out our multiplication by hand, but that is how I work it out mentally. And now I see I erased all my work, and I didn't write my answer. Okay, that did come out to be 345. Alrighty. Now, let's go ahead and continue solving for y. With the y on the left side of the equation, we have a subtraction of 3155, so we want to do the opposite of that subtraction to move it over from the left side of the equal sign to the right. And we get y is equal to negative 23x. And now we have 3155 plus 300 is 3455. 3455 plus 40 is 3495. And now we add in the extra 5. And 3495 is plus another 5 is going to be 3500. And this, at least in terms of x and y, is the function representing this skydiver's altitude. Or we can say that her altitude, that's the dependent variable, right? In terms of the time period going by was in terms of seconds. So her altitude in terms of seconds, and I'm going to turn this around a little bit, is 3500 minus 23 times the number of seconds, and I'm just going to write SEC for seconds because I'm running out of space, and that's how our linear function would look if we wrote it in terms of words, and kind of like more how real people talk. Anything instead of x and y's. Anything look familiar in this equation? The negative 23x, well, that original word problem didn't have any negative 23 anywhere other than it looks familiar because we had to calculate the slope from our 4 points that were in the table of values. But didn't the original problem say something about the plane was at 30, she jumped from a plane or jumped at an altitude of 3,500 feet and then immediately deployed her chute? Yeah, the way the problem was worded, and since we identified the x-axis or the independent variable as time, at time 0, as soon as she jumped out of the plane, that was her altitude. That is the, y equals mx plus b. The wording of the problem gave us the y-intercept. Now, let's interpret the meaning of that y-intercept, and I kind of just already verbalized it. It was the y-intercept is the expected y value, the expected dependent value when the x or the independent variable is equal to 0. When a line is crossing an axis, like we're talking about a y-axis, then the x-coordinate has to be equal to 0. In this case, the x-axis was representing time. So the interpretation of the y-intercept is at time 0. I don't know why I'm writing the word 0 instead of just the number, or when she jumped out of the plane. Her altitude, how far she was off the ground, was 3,500 feet. Okay, so we've talked about reading a word problem and looking at a table of values and identifying, that with the slopes being equal with multiple points, that we were looking at data that could be represented by a linear function. We went ahead and found that slope, like I just said. We have now found the equation that models that situation. We've interpreted the slope and the y-intercept. Let's do a little review of how to graph this on an x-y axis. So, you saw me put the independent variable quantity and units of measure along the x-axis, and I counted by 10 because looking at that table of values, we had I think a data point that had an x-coordinate or an x value of 15 seconds, and another one that went all the way out to 30. So that's quite a large range of values, even if we have an even larger range for the altitude. So I went ahead and I thought in my mind, I was thinking, well, I know we're jumping from a plane. That's of course going to mean that a time of 0 has some real meaning in the context of this problem. And if I have to go all the way out to 130, I'm not going to count by 1s or 2s or even really 5s, and I just thought 10 was appropriate. And then once you set your scale, please don't change it as long as you start to label the x and y axis, the independent and dependent variable. It said in the problem that the altitude was 3,500 again when she jumped from the plane, so we need to go from 0 because it again makes perfect sense in the context of this problem that we'd have an altitude of 0. She's going to land at some point. So we need y values that go from 0 up to that initial value of 3,500. Now in the context of this problem, and all word problems actually, let me rephrase that, for all word problems, when you interpret the slope, it is going to have some kind of real life meaning. Then interpreting the y-intercept, we've already done that for this particular problem. That may have some real life context, contextual meaning, and sometimes not. And then also your x-intercept may or may not have some real life meaning. In the previous example or lesson that we did, there was no real life application or contextual meaning to the x-intercept. Now this one, there will be. After how many minutes will not he, but she land? And actually the answer to this question, at least in terms of seconds and not in minutes, might help you graph this linear function, because when you graph y equals mx plus b, it's very simple. We can see that we're going to have a point at 0, 3,500, but on this scale, trying to count down 23 feet in over 1 second and 23 feet in over 1 second to work out the slope that we have in front of the variable of x, or independent variable of seconds, you're not going to be able to really graph that when your vertical scale goes all the way up to 3,500 units. How are you going to count down by 23? Your best bet is to say, okay, I've already got the y-intercept when x is equal to 0. Let's find another point. And that other point, well, okay, we found the slope a couple times. We found the exact same answer of negative 23. And so we knew that those points were, well, I didn't do every single combination, but we know that those points are falling in a straight line. But if you didn't have a table of values and you said, okay, graph this, y-intercept, x-intercept, let the y be 0, and solve for x. So that's really kind of part of the reason, excuse me, why I included this last example. So 0, her altitude when she lands is going to be equal to 3,500 minus 23, well, I'm going to go ahead and put the x back in there for seconds. And we're going to subtract both sides by 3,500. I like to find my answers algebraically. You can graph this on a graphing calculator and go to second calc if it's an 83, 84, or you can hit menu and analyze graph if you're using a TI-NSPIRE and say that you want to find a 0 or a root, or that's probably what it's going to say in a graphing calculator. 0, root, or solution. Those are all x-intercepts. But then what happens when the next calculator comes along? You don't know how to do the algebra. So we're going to subtract both sides by 3,500, and we get negative 3,500 is equal to negative 23x. We're going to then divide both sides by negative 23 to get it away from the x, the number of seconds that this descent takes. Dividing two negatives gives us a positive answer. And then x, I'm not going to just write a number because this is an answer to a word problem now, is 152.2 seconds. So if I were graphing this equation without a big table of values and I could just plot those 4 points, y-intercept 3,500, let's go to where the x axis runs out to 152, put a dot out there. Where it's 152.2 comma 0, and then draw a line through the x and y-intercept, and that's probably how I would have graphed that if I didn't have those table of values. Now that is going to be 152.2 seconds for the skydiver to land. But the question says, how many minutes is it going to take? Well, I'm going to take how many minutes? Well, there's 60 seconds in a minute. I want to go from a very small time period of 60 or seconds and rewrite it in terms of a longer time period of minutes. And there's 60 seconds in in a minute. So I'm going to divide this by 60 to convert from a very short period of time to a longer period of time. So 152.2 divided by 60. This is 152.2 seconds. We're going to divide that by 60 seconds to convert into minutes, and we get 2.54 minutes. And I meant to wear a watch at the end of this example, just to point out, to say that I don't know what 0.54 of a minute is, except, you know, 0.5 is a decimal version of a half, and a half of a minute is 30 seconds. So maybe we can understand that this 0.25 part is going to be a little bit over 30 seconds. But what I can do now, if I want to write this in terms of minutes and seconds, is I can go, okay, well, there's 2 minutes, and 0.45 of a minute. Well, you know, if I don't want to write that as a decimal, there's going to be some point of a decimal, but I can take the 0.54 and multiply that, kind of take that decimal part at the end of the problem and convert it back into seconds. So I can say, well, it's 2 minutes and 31 seconds, or 32 seconds, or let's see, 0.54 times 60 is going to be equal, you know, off the top of my head, 32.4. So the skydive is going to last from 3,500 feet till the altitude of 0 when she lands, 2 minutes, 32.4 seconds. And if we've all used a stopwatch, we know that stopwatches, you know, after the seconds, will read it a tenth of a second, hundredth of a second, and so on. So that now makes perfect sense. It's a way to write the answer correctly. It's a way that we actually naturally, you know, talk to people, and not just how we talk when we're looking at math or working in a math book. So that is the end of my lesson, modeling real-world situations with linear functions. I'm Mr. Tarrou. Bam! Go do your homework.